welcome and hi. We are now at the last subtopic of chapter 11, Introduction to Particle Physics. What is particle physics? I'm glad you asked. Particle physics is a branch of physics that studies the elementary constituents of matter and radiation, and also the interactions between them. For much of the first half of the 20th century, physicists believed there were just three fundamental particles: the familiar proton, neutron, and electron. We know that proton and neutron are in the nucleus, and we have a cloud of electrons surrounding the nucleus. By the mid-1960s, however, that picture had changed. Improvements to particle accelerator and detector technology had given way to the discovery of seemingly endless list of new particles. Elementary particle physics is the study of fundamental particles and their interactions in nature. Those who study elementary particle physics, which are the particle physicists, differ from other physicists in the scale of system that they study. A particle physicist is not content to study the microscopic world of cells, molecules, atoms, or even atomic nuclei. They are interested in physical processes that occur at scales even smaller than atomic nuclei. Because since then, the particle physicists have discovered that within a proton we have three quarks, which are the indivisible particles that are known as fundamental particles. At the same time, they engage the most profound mysteries in nature. How did the universe begin? What explains the pattern of masses in the universe? Why are energy and momentum conserved? So in answering all those questions, we're going to study particle physics. Thermionic emission. Thermionic emission is a process in which free electrons are emitted from the surface of a metal when external heat energy is applied. In other words, we can say that when you provide heat energy, or when this metal is heated, free electrons, which are the valence electrons from these metals, will be escaping from the attraction of the atomic nuclei. The free electrons gain enough energy and overcome the attractive force of the atomic nucleus, which holds the free electrons in the metal. The free electrons will break the bonding with the metal and jumps into the vacuum. Once they are in this region, they will be attracted to anode, which is positive plate. It is positively charged, so it is no accident that the electrons will be attracted to the positive plate. This thermionic emission process plays a major role in the operation of electronic devices. And we know from our knowledge in previous chapters that the number of electrons emitted from the metal surface depends not just on temperature, but also on the surface area of the metal used and the work function of metal, which is the amount of energy that need to be overcome in order for the electrons to liberate it from the metal. These are some of the applications of thermionic emission. It is used in television receivers, electron emitters, electron microscope, and also in X-rays. X-rays particularly are very useful because it is used in diagnosing broken bones, etc. Let's study about the acceleration of particles by electric and magnetic fields. We know by now that charged particles in uniform electric field will be moving because they are attracted to the corresponding plate. So to create an electric field, we just have to have metal plates of varying potential difference. The plate with a lower potential difference will serve as a negative plate. The plate with a higher potential difference will be the positive plate. If you were to have a positively charged particles, the charged particle will be attracted to negative plate, and the negatively charged particle will be attracted to positive plate. As shown in this figure, this is the direction of electric field. So this is what happened when V is parallel with E, which is the electric field. The charged particles will be undergoing linear motion. But what happens if velocity of the particle is perpendicular to the direction of electric field? The charged particles will be moving in these trajectories, which is known as parabolic path. Electrons are accelerated towards positive plate, and protons are accelerated toward negative plate. What about charged particle in uniform magnetic field? In this example, we have a positively charged particle that is moving in circular motion. This is the result when the positively charged particle, which is a proton, the velocity is perpendicular to the direction of magnetic field. We can determine the direction of magnetic force by using Fleming's left-hand rule or palm rule, and consequently this magnetic force will be pulling the charge in this direction. So in the end, the charged particle will be moving in circular motion as shown in this figure. So we say that charged particles are deflected. So by now we know that charged particles, they can get deflected if there is an electric field or there is a presence of a uniform magnetic field. And when the direction of electric field is parallel to your charged particle, we're going to see a linear motion. However, when the charged particle is moving perpendicular to the electric field, we're going to observe a projectile motion or parabolic path. For a charged particle in uniform magnetic field, when the velocity is perpendicular to the field, it will be moving in circular motion. Okay, what are the rules of electric and magnetic fields in particle physics? They are used in accelerators and detectors. What is the particle accelerator? It is a machine designed to accelerate charged particles. Let me give you one example. If you have a proton in a very high velocity collide with another proton which is also in high velocity, they will be producing amazing new particles. Because in most ordinary collisions, the two protons pass through each other without any significant outcome. However, in about 1 in a million collisions, the two components hit each other violently with such high velocities that most of the collision energy is set free, producing thousands of new particles. So for a particle accelerator, it has two types: electrostatic accelerator, and as the name implies, it uses static electric field to accelerate particles. Electrodynamic accelerator, on the other hand, has two types. The first one is linear accelerator. The second one is circular accelerator, that is known as cyclotron. Linear uses alternating electric field to accelerate particles in a linear beam. So after the particles are accelerated, they will be moving in linear motion. That's why we call it linear accelerator. For circular accelerator, it uses alternating electric fields to accelerate the particles, and after that, the particles will be moving in circular path due to the fixed magnets. Actually, we have another type. that is known as synchrotron. Synchrotron accelerator is the most commonly used in nowadays accelerators, but this is beyond your syllabus. For your syllabus, you just have to be focused on linear accelerator and cyclotron. Particle accelerators use electric and magnetic fields to accelerate and guide beams of charged particles. They can produce precisely controlled beam of particles by that manner, and these beams have three main uses. First, high energy particles can collide to produce new particles. Secondly, a high energy particle has a short de Broglie length, and so it can probe the small interior structure of other particles, because E is equal to hc over lambda. In order for you to see the inside of a tiny particle, we have to have a particle with such high energy, because they are inversely proportional. And lastly, these beams can produce nuclear reactions for scientific or medical uses. Linear accelerator is often shortened as 2-LINAC, is a type of particle accelerator that accelerates charged subatomic particles or ions to a high speed. This is done by subjecting them to a series of oscillating electric potentials, because this C1, C2, C3, and C4, these four chambers are connected to an alternating power supply. This is done to accelerate the charged particle, because the charged particle, it happens to be a proton here. This proton will be attracted to negative, then another negative, then another negative. This is done continuously until at the end of this chamber, the proton will have enough velocity. This diagram shows the working mechanism of a cyclotron, which is a circular accelerator. It is used to accelerate the positively charged particle to high speed. We have two Ds. This is known as Ds because it's in the shape of the letter D, D and another D. And we have a gap between them. In between the gap, it is connected to an alternating power supply, which will produce an electric field that serves as an accelerator to accelerate the charge at each gap. And at the end of this arrangement, there is a fixed target where the charge will hit the target to be detected. So electric field is used to accelerate charged particle, and magnetic field is used to bend the charged particle in semicircle. But what happens to the radius? We know that R is equal to mv divided by qb. Each time the charge crosses the gap, it will be increased in velocity. And when the velocity is increased, the radius also increases. So it goes through the gap, increases the velocity, radius is increased. It crosses the gap, more velocity, radius getting bigger, crosses the gap again, radius bigger, accelerate, then bigger radius, and in the end it will have maximum radius that it can achieve and goes in a straight line to hit the target. Okay, as I explained, for bigger velocity or for higher velocity, we're going to see bigger radius. So this is what happens. This is the top view. And finally, with the biggest radius that a charged particle can achieve, it will travel in a straight line and the beam will hit the target, as shown in this animation. So in between the gap, we have electric field. In these D's, we have magnetic field to deflect the charged particles so that it will move in a circular path. What is a detector? A detector is a device used to indicate the presence of fast-moving charged atomic or nuclear particles by observation of the electrical disturbance. Purpose of a particle detector is to accurately measure the outcome of collision created by a particle accelerator. If we've created particles in a collision in an accelerator, we want to be able to look at them, and that's where particle detectors come in. We'll build this at the collision point in an accelerator. So you see, in this figure, we have negatively charged plate that allows ions to come through, and we have a detector at the end. Most commonly, we build this at the collision point. So when a proton meets another proton, we put the detector right here at the collision points. So the principle of a particle detector is simple. It will never see a particle directly, but shows where it has traveled, what signature tracks it leaves behind, and the effect it has on the detector when it is stopped as it flies out of the collision. And detectors consist of layers of different types of material which are used to either show us the path of the particle as it travels along or absorb it to make the particle stop. It's like a camera. It is a bit like a police investigation after a car crash. If we know what particles were produced in the collision, in which direction they flew, and how much energy they had, we can reconstruct what exactly happened in the collision. So it's all about what happens after, because we cannot actually observe the particle itself. So if we know what happens after the collision, the particle travel here with this much energy, and the other particle travel here as a result of the collision. Reconstructing the particle collision means you can find new type of particles and work out how they interact with each other. And each detector is designed to measure a different aspect of the collision event. For example, one detector might be designed to measure photons and another might be designed to measure muons. This is the accelerator at Fermilab Cyclotron, which is in the US. It is the second most powerful particle accelerator in the world before it shut down on September 29, 2011. It accelerated beams of protons and antiprotons to 99.99954% of the speed of light, around a 4-mile circumference. So this accelerator, which is a circular particle accelerator, discovered 12 quark and 5 baryons. The accelerator at Fermilab uses linear accelerator, LINAC, which is here. It produces negatively charged hydrogen ions, which is the first step in creating proton and antiproton beams. So LINAC is used to produce the hydrogen ions, and this black arrow shows the proton direction. Proton, 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 proton. And this is the proton direction. This is the antiproton direction, which is the antiparticle of proton. Proton and antiproton will collide at such high velocities, and they will collide here. At the collision point, a detector is put. It is placed right here, and the detector is called D0 detector. The proton and antiproton collisions created showers of new particles, and the detectors more than 2 million times a second. For interesting events, the detectors recorded each particle's flight path, energy, momentum, and electric charge. Alright, now this is the accelerator at CERN, European Organization for Nuclear Research, which resides between France and Switzerland countrysides. It was one of Europe's first joint ventures and now has 23 member states, and that includes around 10,000 scientists. The instruments used at CERN are purpose-built particle accelerators and detectors. Accelerators boost beams of particles to high energies before the beams are made to collide with each other or with stationary targets. Detectors observe and record the results of this collision. This is a picture of one of the accelerators at CERN. So you can see the magnitude of the accelerator. We have a person right here, so you can see the perspective. And this is the map of CERN. This is the map of LHC. CERN refers to the lab. The LHC tunnel is located 100 meters underground. It has to be constructed underground because when charged particles are accelerated, they give off radiation, and to prevent that radiation from entering human beings or anything, it is constructed underground. And for this LHC, which is Large Hadron Collider, is very literal. It means that this is the place where hadrons will collide. Hadrons refer to protons in this case. The majority of its length is on the French side of the border. It uses the 27 circumference circular tunnel. The circumference is 27 km. So CMS, ALICE, and ATLAS are some of the detectors used. And this would be the accelerator, where the accelerator is. CERN Hadron Linacs are linear accelerators that accelerate beams of hadrons from a standstill to be used by the largest circular accelerators at the facility. So LINAC 1 operating from 1958 until 1992, and the most recent one is LINAC 4, replacing LINAC 2 in 2020, accelerates negative hydrogen ions, which are the source for protons to be used in the experiments. Now, this is the map of LHC. In CERN, it operates a network of 6 accelerators and a decelerator. Each machine in the chain increases the energy of particle beams before delivering them to experiments or to the next, more powerful accelerator. So LINAC 4 is used to accelerate particles. We start with hydrogen ions, and then it became protons, and it goes through proton synchrotron, PS, where they are boosted with high velocities. And this blue arrow shows the path of the protons. So the protons will be traveling here. The other protons will be traveling here. So the amount of protons in LHC is 10 to the power of 11 protons, because it is not easy for the protons to collide due to its very tiny size. And like huge 3-dimensional cameras, the detectors here, for example ATLAS, ALICE, and CMS, they gather information on those new particles, including their trajectory, electrical charge, and energy. And for the collisions, it's in about 1 in a million collisions. So the odds of having a collision is 1 in a million, and to add to the difficulty, the particles we're looking for may be unstable and decay into more familiar particles before reaching the sensors. So it's not easy for the protons to collide. That's why we have a huge amount of protons traveling around the tunnel. And ATLAS, a toroidal LHC apparatus, is the largest general-purpose particle detector experiment at the LHC, which is a particle accelerator at CERN. The experiment is designed to take advantage of the unprecedented energy available at LHC, and as of right now, the amount of energy that is used is 7 tera electron volt. This detector enables physicists to observe phenomena that involve highly massive particles, which were not observable using earlier lower energy accelerators. As of right now, Accelerator at CERN is currently in a long upgrade process. It is closed for maintenance, so that it will be equipped with more cutting-edge versions, and it is planned to be back online in summer 2021, which is around June this year. And then it will have another 2-year shutdown before LHC comes online on 2027. So this is the screen that is available on CERN website, and if LHC is online, you can see the data that is obtained by the LHC at real time. Previously, we have discussed the need of high energies required to investigate the structure of nucleon, because only high energy particles produced in the accelerators are used to investigate the structure of nucleon described. From the Broglie wavelength, lambda is equal to hc/E. We know that the greater the velocity of the particle, the bigger the energy is, and the shorter the wavelength, and the more detail can be obtained in terms of new particles. And the high energy particles produced in the accelerator also used to produce and study many types of particles that we're going to study in the next few slides in standard model of particles. The universe is made up of matter, and molecules are the basic constituents of any chemical compounds. An atom is the smaller version of molecule, which is what we have on periodic table. So we have many atoms in the periodic table, and in an atom we have a nucleus and a cloud of electrons. An electron is the first particle that is discovered to be indivisible particle. It means that when you break the electron or you cut it in two, you won't see anything inside. Electron is an indivisible particle. But for a nucleus, when you cut it in half or you break it down, you're going to see smaller particles. And those smaller particles are known as elementary particles. The Standard Model is the name given in the 1970s to a theory of fundamental particles and how they interact. It incorporated all that was known about subatomic particles at the time and predicted the existence of additional particles as well. There are 17 named particles in the Standard Model. It organized into the chart shown below. The last particles discovered were the tau neutrino in 2000, tau neutrino, which is this one, and the Higgs boson in 2012. So what are the Standard Model particles? We know that in a nucleus, we have proton and neutron. So this nucleus is not the smallest types of particle that we can observe, because through experiments we found that in a proton you have 3 quarks, up, up and down. And these quarks are the most elementary particles, because when you cut it in half, you won't see anything inside. It is the smallest particle there is. And for quarks, we have 6 flavors: up, down, charm, strange, top, and bottom. They come in a wide range of masses. In the first column, the first generation being the lightest ones, the second column heavier, and the third one being the heaviest. For leptons, the first one discovered was electron, and then we have the siblings, the heavier siblings, muon and tau. Why are there 3 and only 3 different versions of each of the particles? This remains a mystery. We don't have any idea of the answers, because for the standard model particles, we have 1, 2, 3 generations, and only 3. These heavy particles are only produced for very brief moments in high energy collisions. That's why we don't see it in everyday life, and this is because they decay very quickly into the lighter particles. Such decays involve the exchange of force-carrying particles, which is known as gauge bosons. We have W and Z, which, unlike the photon, is not massless. They carry the weak force, which is the final force of the standard model. This same force allows protons and neutrons to transform into each other, W and Z, and this is used in beta decay, which is a vital part of the fusion interactions that drive the Sun. To observe the W and Z directly, we needed the high energy collisions provided by particle accelerators. G, gluon, is the one responsible for strong force. What is strong force? Strong force is the force that responsible to bind proton and neutron in a nucleus. And photon carry the electromagnetic force. Electromagnetic force. Photon is massless, but gluon, W and Z bosons does have masses. And lastly, we have the particles, the last particles, another kind of standard model particle, and these are called neutrinos. The first one is electron neutrino. So these neutrinos are associated with the corresponding lepton. Electron neutrino, muon neutrino, tau neutrino. These only interact with other particles through the weak force, and trillions of neutrinos, many generated by the Sun, fly through us every second. But we don't feel it because neutrinos have no charge and they didn't interact, or they don't interact with other particles. That's why it's very difficult to discover these neutrinos. Measurements of weak interactions found that there are different kinds of neutrinos, as I just explained. And the last one is Higgs boson. That is related to Higgs field. To understand about Higgs boson, you have to know what is Higgs field. Higgs field is a hypothetical invisible field that pervades the universe. It gives mass to elementary particles, and when a particle passes through the Higgs fields, it interacts and gets mass. Have you ever wondered about mass? where this mass comes from or why they have the masses they do, and this is the answer. Because when a particle passes through the Higgs field, it interacts, and the more it interacts, the more mass it has. For instance, quarks interact strongly with the field, gaining relatively large mass. Electrons only interact slightly, and so they are extremely light. And photons, which have no mass, it is because they don't interact with the field at all. And Higgs field is the one responsible to give mass to everything, every matter in the universe. And Higgs boson is an excitation of Higgs field. It's an excitation of Higgs field. By finding the Higgs boson, we know that Higgs field exists, and without Higgs field, we don't have any masses. These are the particles that produced in high energy reactions: quarks, leptons, fermions. Bosons are the categories. Fermions meaning the particles have half spin or intervals of half. It could be half, 3/2, 5/2. Bosons, which are the force carriers, for example, photon, W and Z particles, gluon, they are particles with integer spin. Integer meaning they have 1 spin or 0 spin. We have 6 quarks: up, down, charm, strange, top and bottom. And for every particle, we have an antiparticle associated with the particle, and the antiparticle have identical properties except that they have opposite charge. For example, electron, the antiparticle is anti-electron or positron. So they are identical except for their charge. Electron is a negatively charged particle. Positron, it has the same mass, but it is a positively charged particle. Up, we have anti-up. The symbol is written like this. We have an over bar. Down, anti-down. Charm, anti-charm. Strange, anti-strange, and so on. It's not only restricted to electron. For electron neutrino, we have the antiparticle anti-electron neutrino. Anti-electron neutrino. Muon is anti-muon. Muon neutrino is anti-muon neutrino, being the antiparticle. There's another way to categorize the standard model particles. We have hadrons. What are hadrons? Hadrons are the particles that have quarks inside. So if a particle has quarks inside, like proton, proton has 3 quarks, up, and down. So we can call proton a hadron. Hadrons can be divided into 2, baryons and mesons. Baryons is a type of particle that consists of 3 quarks. So you guess it, proton is also a baryon. Mesons are particles that comprise of 2 quarks, but it has a condition. Those 2 quarks have to be a quark and an anti-quark. Let me give you some examples. We have proton. The components of a proton is U, U, D, up, up, down quarks. Neutron, U, D, D, up, down, down quarks. What about mesons? We have Neutral pion. Neutral pion is the name. And you don't have to remember the names, you just have to know the category or the types of quarks. Neutral pion, the components are U over bar. It means that the particle has a quark and an antiquark inside it. So we call neutral pion a meson. This is another summary for standard model of particles. Fermions are for particles that have spin half. So leptons and quarks are fermions. Baryons are also fermions. Mesons, since they have spin 0 and 1, which are integers, we call it bosons. And bosons, this is gauge boson or the force carriers, photon for electromagnetic interactions, W and Z, bosons for weak interactions, for example beta decay, beta plus or beta minus, gluon for strong force. What is the future of particle physics? This is something that you have to think. If you are interested in pursuing particle physics, maybe these are the future works that you can do. New exotic particles have been discovered. They are known as tetraquarks, which consist of 2 quarks and 2 antiquarks, and pentaquarks, which have 4 quarks and an antiquark. The new tetraquark is dubbed as, which is the name it's called, is X6900. 6900 being the mass of the tetraquark. And in June 2020, the Consortium of Europe's top particle physicists published their vision for particle physics. And a big part of that is future circular collider, which will be able to accelerate particles 4 times than LHC. And what do we know about energy? High energy particles will be able to produce more tiny particles. So we might be able to discover new particles which are smaller than electron, which are smaller than up and down quarks. If it happens, it will accelerate particles with 100 km circumference underground and circling Geneva. So this will be nearby to LHC or CERN. It will be beneath the Swiss and French countrysides. And lastly, we are now still searching for a theory that unifies our understanding of the standard model particles and forces, as explained by standard model, because standard model just explain strong force, weak force, electromagnetic force. But remember, we have another one, which is gravity. It has not been discovered as of yet. Gravity, the gauge boson responsible is graviton. If we are able to find graviton, we can conclude everything for TEO, theory of everything, theory of the universe. And these are the future works that can be done. So this would be the end of chapter 11. All the best for your exam and good luck. Thank you.